Alright, so today we're going to be discussing photons, the photoelectric effect, and wave-particle duality. To start, we'll discuss the quantum mechanical model. Quantum mechanics describes the mechanics or behaviors of materials and particles at a subatomic level. This includes the subatomic particles protons, neutrons, and especially electrons. Before quantum mechanics, physical interactions between particles were what we call deterministic. This essentially means that the present has a direct effect on the future. Any scenario with absolutely constant variables will yield the exact same result every single time. Quantum mechanics changed this perspective, and a good example of how this works is the following experiment. An electron fired along a line can be measured to make contact with a specific point on a surface. Another electron fired in the exact same way and under the exact same conditions will make contact with a different point. Even leading quantum theorists like Albert Einstein were confused and unsettled by this kind of behavior. One of the other of these leading quantum theorists was Schrödinger. Schrödinger studied quantum mechanics in the early 20th century, and they proposed a scenario to explain the confusing nature of electrons. When unobserved, quantum particles can exist in two states simultaneously. By nature of our observational methods, observing those subatomic particles actually forces them into one of those two states. If you're confused, don't worry, because we are too. And Schrödinger actually came up with a great example to explain this. And so we're going to talk about Schrodinger's cat. This was a thought experiment that was never actually done, but instead used simply to explain quantum theory. In this scenario, a live cat is placed inside a sealed container, and in the container with the cat is a radioactive substance. After a certain amount of time, a single subatomic particle of this substance has, with equal probability, either been ejected as radiation or has done nothing. Thus, it either has a position away from the substance or is still part of an atom in the substance. If the particle has ejected, it will trigger a weight to smash a vial of poison, killing the cat. If the particle hasn't ejected, the cat remains alive. After this length of time has passed, the particle exists in a quantum state, occupying both an ejected and not ejected state. Thus, the weight also exists in a quantum state, and by extension, the cat is both alive and dead at the same time. By opening the box, we force an observation of the cat, which obviously demonstrates if it is alive or dead, thus resolving the quantum states of all of the other components in the box. If you're still confused, don't worry, we are too, and so is just about everyone else. So let's leave the confusing stuff behind for a little bit and talk about light. While quantum mechanics focuses primarily on electrons and other subatomic particles, it also applies to light. Light actually exhibits properties of both particles and waves, earning what we call wave-particle duality. Let's start with the wave nature of light. First, let's establish what light really is. Light is a form of energy, just like electricity and kinetic energy. This type of energy is called electromagnetic radiation, which is embodied by oscillating fields of magnetic and electric energies. In a vacuum, these waves propagate at c, or 299,792,458 meters per second, or about 3 times 10 to the 8th meters per second. At this speed, light can travel around the world in about 1/7 of a second. These waves, like all others, are characterized by amplitude, frequency, and wavelength. The wavelength is represented by lambda, frequency is represented by nu, and amplitude is represented simply in terms of distance. This photo illustrates the different parts of a wave. Peaks and troughs represent the high and low points along the wave, and a wavelength refers to the distance between two peaks or two troughs, and the amplitude refers to the height difference between peak and trough divided by 2. On a sine wave, the wavelength is 2 pi and the amplitude is 1. In light, higher wave amplitudes result in brighter light. Wavelengths directly affect and control the color of light, and this is measured in standard units of length as well. Frequency is inversely proportional to wavelength and is measured in revolutions per second, or hertz. Alright, so light is an electromagnetic wave, but let's learn a little bit more about electromagnetic energy before we revisit light. There are a lot of different types of electromagnetic waves, each having a different wavelength on a spectrum as well as a different energy. What we call the visible range of electromagnetic radiation lies between 400 and 700 nanometers of wavelength. Smaller wavelengths move faster and have more energy, like X-rays and gamma rays. These forms can damage cells due to their high energy. Microwaves, which are not shown on this image, are weaker than infrared and stronger than radio waves. In short, standing in front of the microwave is actually less dangerous than your regular house lights. Alright, so finally the part we've all been waiting for. Colors. Let's talk about colors. So since light colors differ a bit based on their wavelength, it would make sense that each color has its own wavelength. Violet light has the shortest wavelength and thus has the highest energy. UV light is just above violet on the spectrum and is thus called ultraviolet. Red light, on the other hand, has the longest wavelength and just the least energy, and IR lies just above red on the spectrum and is thus called infrared. But if light is on this rainbow spectrum, why doesn't all light look like rainbows? See, unlike paint and dyes, light combines additively. Wavelengths of light are added to form new colors, whereas paints and dyes subtract wavelengths when they are added. Light operates on three primary colors: red, green, and blue. Adding these colors yields white, as colors get lighter as more wavelengths are added. Paints, however, work on three different primary colors: cyan, magenta, and yellow. These three colors yield black, or K. When pigments are added, colors get darker as more wavelengths are added. This is actually where the RGB and CMYK color systems came from for use on computers. Finally, we'll get to the first of a few dad jokes in chemistry. Don't worry, you'll learn this stuff on this slide too. So here we go. The relationship between frequency and wavelength can be described as nu equals c over lambda, where nu is the frequency, c is the speed of light, and lambda is the wavelength. To help you remember this formula, just use this admittedly terrible joke, and please trust us when we tell you it works. Here we go. What's new? C over lambda. Terrible, I know, but wait, because it gets worse. There's also the inverse of the joke, which makes even less sense. What's lambda? C over nu. Okay, jokes are done. Next up, though, is interference. This term refers to the interactions of light between different wavelengths. It is an additive process where wavelengths combine with one another. Constructive interference occurs when two waves in phase, meaning that their peaks and troughs are aligned, combine to result in a wave with twice the amplitude. Destructive interference occurs when two waves are out of phase, meaning that their peaks and troughs are not aligned, and results in the interference of light. Two of the same wavelengths that are perfectly out of phase will negate one another, and no light whatsoever will be emitted. Here we're going to discuss three phenomena of light. Dispersion refers to the ability for white light or other combined colors to disperse into many separate wavelengths when passing through a prism. Diffraction refers to the ability of light to squeeze through narrow openings, creating interference as it passes through. Refer to the double slit experiment for more information on this phenomenon because it's really very cool. And refraction refers to the effect that translucent materials have on light, effectively bending it to create illusions of perception or depth. You can see visualizations of these phenomena in the picture below. Okay, so all we've been talking about so far indicates that light is a wave, right? If you believe that light is a wave, guess what? You're wrong. Okay, sorry, no, you're half right. But if light is a wave, how can it also be a particle? To figure that out, let's move to the photoelectric effect. The photoelectric effect is one of the main proofs of the particle nature of light. In a photoelectric experiment, a beam of light called the incident beam strikes a metal surface, causing electrons to become excited and emitted from the metal. The electrons are only ejected when the incident light energy exceeds the bond energy of the electrons. According to wave properties of light, electron emission should depend on the intensity or amplitude of light. Scientists expected low-intensity rays to take more time to eject electrons since the energy would need to build up before exceeding the electron's bond energy. Instead, they found something unexpected. So what did they find? Rather than taking time to eject electrons, light striking a metal surface is observed to only eject electrons when the light meets or exceeds what we now call the threshold frequency. Below this frequency, no electrons are emitted regardless of time or light intensity. If this is confusing, think about it this way. The electron's bond energy is like a glass window. It requires a certain amount of force to break. If you throw a ping pong ball at it, nothing will happen. Throwing one ping pong ball every second for 1,000 years will still have no result. Even throwing 1,000 ping pong balls all at once will have no impact. In this example, a ping pong ball represents light without a high enough frequency. Increasing the time or intensity, the amount of light particles or ping pong balls, has no effect, but throwing a baseball out a window will break it. Of course, in this example, the baseball has enough frequency to eject the electron. So how do we explain this phenomenon? Well, Einstein proposed that light is quantized, or comes in discrete units, packets, or particles. The amount of energy E in one of these packets of light depends on its frequency according to the equation E equals h nu, where h is Planck's constant, which is equal to 6.626 times 10 to the negative 34th power in joules seconds. This explanation of light as a particle satisfies the experimental results, where the emission of an electron depends on whether or not a single photon in a packet or quanta has enough energy to overcome that emission threshold. So we can now finally see that light is a little weird. It can be reliably explained as both a wave and a particle. So to settle the debate over the nature of light, science made a compromise. Light is now accepted as both of these things at the same time. However, by nature of quantum mechanics, we can't use light as both of these things at the same time, as observing the nature of light will force it into either a wave or particle form, depending on the observation method. So when we need light to behave like a particle, equations in experimental design can be tailored to make it behave just like a particle. If we want it to behave like a wave, we can do that too. Alright, that's all I have for this video. Thank you.